Today, we are working on solving logarithmic equations. Here, we'll be considering the laws of logarithm in solving some of our equations. Let's take some examples to see the application of these laws. Let's take, for instance, log 121 to base x. Now, from this, we can rewrite this as log 11 times 11 to base x. That will give me log 11 raised to power 2 to base x, which will give me 2 log 11 to base x. Now, in this case, if I have that, therefore, my logarithm here, provided I'm given, but provided now that the log of 11 is not given the particular value. So here I have been able to justify the use of log 3 here, giving me 2 log 11 to base x. Then the other way to work it to see the application of log 1 here, I can take it as log 11 to base x plus log 11 to base x. So I have 2 of the same value. That will give me 2 of log 11 to base x. Meaning if I'm going by log 1 or I'm going by log 3, I'll still arrive at the same answer. Let's take more examples to confirm our workings. Let's consider log 1 over 64 to base 2. Wow. In this one, okay, let's have it being equals to 3x. Going by log 2, this will give me log. Okay, let's first of all take it this way. This will give me 1 over 4 raised to power 2. I mean 4 raised to power 3 there. From there, I will have log 4 raised to power minus 3 to base 2 equals to x. Then from there, I can have it as minus 3 log 4 to base 2 equals to 3x. Or in a better way, if you notice, this my 64 can also be taken as, okay, let's just continue and finish this one first. This will give me minus 3 to log. This 4 can further be broken down as 2 raised to power 2 to base 2 equals to 3x. Then from this place, I have minus 3 times 2. The power 2 here is coming to the back, just as we follow the case of log 3, giving me log 2 to base 2 equals to 3x. So from here, I have minus 6 times log 2 to base 2 equals to 3x. And note, log 2 to base 2, following the log 4, when we have the base of the same log. So we have minus 6 times 1 equals to 3x. Therefore, minus 6 equals to 3x. From this situation now, you notice that we are already at a linear equation where minus 6 being equal to 3x is the same thing as 3x being equal to minus 6. So we divide both sides by 3, giving me 3x over 3 equals to minus 6 over 3. That will give me x being equals to minus 2. So the value of x is 2. Let's consider more examples, more questions for our example. All right. This being clear, I would like us to go into this particular question where we have log x plus 1 being equal to log x plus 1. Whereas in this case, I'm having my log x plus 1. And here I'm having my log having x plus 1 as a whole together. Now, here I can describe this as my log x to base 2. For this can be taken as log 2 to base 2. So in this case now, I will be having my log x times 2 refined back to log 1, so to base 2, which will give me log 2x to base 2, meaning my log x plus 1 to base 2 is giving me my log 2x to base 2. So in other words, I am having my log x plus 1 to base 2 is equal to my log 2x to base 2. So, which justifies that my x plus 1 equals to 2x, as this is showing that an expression indicating this value equals to this value in this case. So, therefore, I will have my, let's collect like terms here at this junction, collecting like terms. We justify that x minus 2x equals to minus 1. So that will give me minus x equals to minus 1. Therefore, I have my x equals to 1. How do I justify that? I have here, I can divide both sides by a coefficient of negative 1 or multiply both sides through with a negative 1. So doing that, let's just use multiply both sides with minus 1. So we have minus x times minus 1 equals to minus 1 times minus 1 to give me x equals to 1. So with that, we have the value of x giving us as 1. Some other thing we can also try to look into or justify here under logarithmical equations. If I have an equation such as 2 log x plus 3 log x equals to 10. Wow, this I can reverse as, or just let us work it further. We have 2 of log s and 3 of log s, giving me 5 of log x being equals to 10. Okay, with that, that's justified that I have log x raised to power 5 being equals to my 10 here. At this junction, we are trying to get the value of x there, where the base being not given from the question shows that it's a log to base 10. So what is 10 to a logarithm? That will give me log that's 10 raised to power here I have 5 log x equals to 10, which means 5 log x to base 10, because we're not given the particular base, meaning it's in common log to base 10 equals to log 10 raised to power 10 to base 10. I'm converting this 10 to log 10 raised to power 10 to base 10, so that I can have log s raised to the power 5 equals to log 10 raised to the power 10. So which justify that my s raised to the power 5 is my 10 raised to the power 10. If I have 10 raised to the power 10, which means I'm having x raised to the power 5 equals to 10 raised to the power 10. To find my x, I will find the fifth root of both sides. So fifth root of x raised to the power 5 will give me x, which is equals to fifth root of 10 raised to the power 5. Then converting that to an index form, I will have 10 raised to the power 10 all raised to the power 1 over 5. So the power in and the power outside will multiply themselves according to the rules or a law in the law of indices, which will give me 10 raised to the power 10 times 1 over 5, which will give me 2. So therefore, my s equals to 10 raised to the power 2. So if my s equals to 10 raised to the power 2, my 10 raised to the power 2 therefore is 100, meaning my s equals to 100. Now that is example 3. Here is another example I will call example 4. If log 5 equals to 0.6990 and log 3 equals to 0.4771, find the value of log root 15. Log root 15 from my solution, as we know, my root 15 according to indices can be written in another form by writing 15 raised to the power 1 over 2. So if I have 15 raised to the power 1 over 2, so log 15 raised to the power 1 over 2 according to the log 3 of logarithm, that would be half log 15. So my log 15 now, according to law 1 of indices, of logarithm, I can write it as 5 times 3. Now I am going back to the question given to us. So I can now replace log 5 with 0.6990 plus my log 3 will be 0.4771. And that will give me half into 1 plus 0, 1, 7 plus 7, and 7 plus 9, giving me 16, remainder 1. Bring that 1 to this, that is going to make it 8. 8 plus 9, giving me 17, remainder 1. Bring that 1 to this, that is going to make it 5. 5 plus 6, that is 11. 1, remainder 1. Dot. My 0 plus 0 give me 0. The remainder 1 will be added here to give me 1. So that I can now have my half to be written as 0.5 times 1.1761. So from here, I can re-explain this as 1.1761 times 0.5. So 5 times 1, 5. 5 times 6, 30, remainder 3. 5 times 7, 35 plus that 3, giving me 38, remainder 3. 5 times 1 is still 5 plus that 3, 8 again, dot 5 times 1, 5. Meaning my log 15, root 15 will give me 5.8. Oh, sorry, there's a mistake there. That will be 5 times this way, 5 times 1, 5. So I can now have 0 times every value will give me 0, 0, 0, 0 all true. So I'll be having 5, 0, 8, 8, 5. Now I have 1, 2, 3, 4, and 5 decimal places. So I will have 1, 2, 3, 4, 5. So that will be 0.58805. So that is to say I have the log of root 15 to give me 0.58805. Thank you. Here I would like to pull the curtain for the topic logarithmic equations. Thank you.